Okay, let's have a look here. Ideas. Okay, yeah, how about that? Let's look at something here. Now, this is not a function of x, right? But let's quickly review a couple things from Algebra 2 and probably pre-calculus as well. How do we come up with the inverse of a relation? What's our recipe for finding the inverse of a relation? What did we do? Remember? What do you mean by that?
I don't know. It makes sense in my head.
You do that. You're right. But what does that mean? Oh, okay. You switch x and y, right? You flip x and y, and then you just isolate the new y, right? And that gives you, does that make sense?
Yeah. Why don't you have to flip the dy dx?
Okay, hang on. Okay, so we were always doing this, though, when we were finding, previously, we had kind of contrived problems where they always work out to be inverse functions. But what if they don't? This is actually the inverse of what function?
Y equals x squared.
Y equals x squared, right? This is the inverse relation of y equals x squared. Now, do you remember back to, I gave you guys a really good little trick for generating the graphs of inverses. Do you remember that? A combined twist and a reflection?
No, but really quick, are you recording?
That's it. Okay, remember this always works.
But are you recording?
I am recording, yes, thanks. Okay, this always works. If you want to come up with the graph of an inverse based on the original graph, you always just rotate it 90 degrees clockwise and then reflect it over the new y-axis, right? That always works. So what does this look like then? This starts off as, so this one starts off as, if we start with the original relation y equals x squared, that's just an up and down parabola, right? Okay, so what happens if we rotate this thing 90 degrees and then we, hang on a second, what happened here? We rotate it other way, sorry. We rotate it counterclockwise 90 degrees, don't we? Yeah. Counterclockwise 90 degrees and then flip it over the x-axis, right? So that means it's going to be a sideways parabola opening to the left, and then we reflect it over the y-axis, and so it ends up being a sideways parabola opening up to the right. So this is the relation x equals y squared, right?
Right.
Okay, so do we see some issues here? Now, if I want to calculate dy dx, this isn't even a function, right? So if I want to calculate dy dx at, for example, x equals 2, I'm going to get back two answers, aren't I? Because when x equals 2, there are 2 points on our relation corresponding to that. It violates the vertical line test, right? It's not a function. Okay, so there was a good idea, though. What was your idea?
Take the square root.
Okay, what if we solve for y? If we take this original relation and we solve for y. There's a lot of good stuff going on here, so really soak this in because there's a lot of really, really good math happening here. So if we just do the algebra where we take x equals y squared, and we're going to maybe turn that around so we get y squared equals x, and then to isolate y, to solve for y, we all know what to do. We take the square root of both sides, right? So that's going to give us y, oh, that's not y. That's going to give us y equals what? Plus or minus the square root of x. Okay, now the math gods are really wise. They know what they're doing, those math gods. They gave us that plus or minus for a reason. What they did here was they in their infinite wisdom, said, okay, this is not a function taken all together. But whenever I go through the process of solving for y and I get multiple solutions, those multiple solutions correspond to the different pieces of the relation that individually are functions, right? So if we cut this thing in two and we treat it as either plus the square root of x, which looks like this, So we could, really, this just becomes either y equals the square root of x, or y equals minus the square root of x, right? Plus the square root of x is this function, and it is a function, right there, isn't it? Minus the square root of x is this function right there. Separately, they work, don't they? Right? So all I really have to do if I want to calculate dy dx then is just differentiate each of these separately, right? So if we take the blue one, and that's just an x to what power? 1/2. Okay, so then dy dx equals what? Okay, good. So 1/2 x to the negative 1/2. Same thing as 1/2 times the square root of x, right? Everybody agree?
Yes.
Right?
Yeah, yeah.
Because it's 1/2 x to the minus 1/2. X to the minus 1/2 means goes to the bottom, and x to the 1/2 is just the square root of x.
So, but you could have just written it here.
Yeah, you could have written it out. I skipped some steps there. What about the other part of this? Well, the only difference is I'm just gonna have a minus sign, right? Okay, so I'm gonna write that as dy dx equals minus 1/2 times the square root of x, right?
Yeah.
Okay. Does that make sense? Because it's just gonna be negative, the minus one's out front, and then I've just got a 1/2 x to the minus 1/2. Right? Make sense? Okay? That's inconvenient though. We don't always want to do that. In fact, many times we can't do that. Sometimes we get relations that are so complicated that it is practically or realistic. I mean, it either is practically impossible, maybe it's really is algebraically impossible to solve for a variable. And so this strategy absolutely doesn't apply. I'll give you an example. I double dog dare you to do this one then, using the same kind of logic. What if we had the relation x squared y to the 3/2 minus 2 times the square root of x cubed y to the 4th plus 3x squared y equals 7, and I want you to calculate dy dx. Go ahead and solve for y.
Okay.
Got it?
Easy.
Yeah, right. That's,
We're done.
okay, you can't do it. You can't do it.
You
No, you can't. You can't solve for y there. It's impossible to separate those variables and solve for y. So, I mean, there's some strategies, incredibly complex strategies you could use to try to break this up into sub-functions, but it was just a nightmare. So, long story short, that strategy is oftentimes not a good one. So we want to go back now and we want to see if there's a way that we maybe could have done this more easily without explicitly solving for y. This is what we call, by the way, an implicit relationship, because y is not isolated by itself. We took this implicit relation and we solved for y to turn it into two explicit functions of x, right? And then we did what's called explicit differentiation, which is the only kind we know how to do up to this point. We only know how to take derivatives of explicit functions of x, where y is by itself and it's equal to some function of x, right? Everything we've done has been that way, correct? This is different. This time the x's and the y's are mixed up together. So what we're looking for here is a way of doing something called implicit differentiation. We want to be able to skip the whole process of solving for y and just differentiate without that process, right? So that's really the title of what we're doing today. It's implicit differentiation. There we go. Okay, so I'm going to rewrite this very subtly, and I want you to see if you can come up with something with a pattern here. Okay, so let's do this.
What, can you go off with that?
Sure. Mhm. Okay, so,
Thank you.
yeah, I gotta check that periodically. Yeah. So, I'm gonna rewrite these very subtly here. I'm gonna rewrite these as dy dx. I'm gonna just call that a y prime, how about? Same thing, right?
Yeah.
So this, I'm gonna rewrite this as y prime equals 1 over 2 times the square root of x. And this one over here, I'm gonna rewrite as, I'm just gonna group the negative sign a little differently. I'm gonna write it as y prime equals 1 over 2 times minus the square root of x. Okay?
What do we do?
All I did, this one I didn't change at all. I just made it a y prime. But look what I did here. I took the minus sign, and instead of writing it as a coefficient out in front, I grouped it with the square root of x. Why did I do that probably, huh? Why did I do that? I don't know why I did that. I'm just not sure. See if you can come up with a reason. Yeah, you have an idea?
Because it's the plus or minus comes from like different.
Well, okay, the plus or minus came when we took a square root of both sides. Say it again.
It's the y.
Ah, there it is. Okay, look. Depending on how we define the y, right? When we explicitly solved for y, we got two answers. We either got y equals the square root of x, in the blue case, or we got y equals negative the square root of x in the red case. But the answers that we got here, if we rewrite those in terms of y, look identical, don't they? Right? So red and blue makes purple, right? So look how slick this is. This is what they teach you in teacher college. This is really good stuff. We could rewrite both of these as y prime equals 1 over 2y.
Can you scroll up?
Yeah.
With all of the points. I just need the.
Just like tell me when to stop. Okay?
I don't understand.
Okay, no, you're going to in a second.
Okay.
You're going to in a second because I want to remind you where this came from. So all this stuff that we did over here on the left side was a pretty long process, right? We're only seeing even part of it because we actually solved for y. But we started off with this. We started off with y squared equals x. Okay, now my question to you is, can you think of maybe a way that we could go in one step? We could go from there to there instead of having to do that whole process of solving for y, taking each case separately, right? That's long and tedious and oftentimes won't even work.
What is it called?
Implicit differentiation.
No, the thing that we just did. Divided
Yes.
by the x.
That's it, implicit differentiation.
No. Last chapter, what was that? Do you
Oh, chain rule?
know?
Derivative?
Yeah.
Yeah. Yeah, the derivatives, yeah.
Yeah, that's what you're trying to do. Can you just
Okay.
divide it by the exponent, like 1 over?
Okay, so say it again. Gino, go ahead.
Can you multiply the variable by like 1 over the exponent?
I can't do that because that's changing things, that's out of bounds algebraically. But could I think back to stuff we've already done? Could I just use the chain rule, right? Why did we necessarily have to solve for y? What if we just differentiated both sides with respect to x using the chain rule? That's fair. Now that sounds a little strange, but what are we going to get on the left side if we just differentiate with respect to x? Now how many layers are there to this problem? Two, right? Maybe 3.
Maybe 3, what do you?
Well, we'll see. I mean, actually it's 2. It's 2, you're right, it's 2. Okay, no, it's 2. Okay, you gotta be riveted up here though, because this is big. So if I want to differentiate this at the outermost layer, that is just hand squared, right?
Yes.
Okay, what's the derivative of hand squared?
2 hands.
2 hand to the 1, right? So step 1 is if I differentiate this, I'm gonna get 2y to the 1, right? I'll make this 1. We don't write the 1, but it's there, right? Times the next layer. Well, when I peel that away, I've got a y. What's the derivative of that with respect to x? Y prime, right? It's dy dx, right?
Yeah.
Okay, because it's not an x, when I differentiate it, it doesn't just become a 1, right? We actually, by the chain rule, I have to differentiate the inside with respect to x, and that's a something, because that's not an x. So when I differentiate something that's not an x with respect to x, that's a rate, right? That's a derivative. So the second layer of this is dy dx. Now, hold on, we'll contrast this with a normal derivative, right? Like if we go back to the good old days of like last week, if we did something like this, if we said y equals x squared, and I differentiate both sides, what do I get on the left? Yeah, dy dx, right? That's what I'm doing, is differentiating both sides. So this side just gives me dy dx, and by the chain rule, this side gives me 2 times hand to the 1, and then times the derivative of x with respect to x, well, what's that? 1. We don't write it, but it's there, right? Make sense? See the difference? This time, though, we differentiated, instead of differentiating x squared with respect to x, we differentiated y squared. So it's not a 1. We get 2 times y to the 1 times, not dx dx, times dy dx, right? Okay?
So it's like y to the 1 always dy dx now? I don't get how we did
Yeah, the derivative of y we've never really thought about it that carefully or that closely. We've never needed to, but haven't we always done that? If we start off with y equals something and we differentiate, we get dy dx equals something, right? Okay? Yes?
Wait, but then how do we get to the purple?
How do we what?
How do we
Okay, well, we're not done. We didn't do the other side, did we? So this is what we get from that side. What's dx dx? 1.
Why is dx dx 1?
Well, what's that look like?
1.
Yeah, same thing on top, same thing on bottom, right? And that's a rule of ours. If we differentiate x, take the derivative of x, we always said we get 1, right? For that reason, actually, though, because it's dx dx.
What if you take the derivative of y, you get y prime?
You get y prime. Exactly, you get dy dx, right? Okay, so now I'm going to erase this part. Need a little more room. And let's rewrite this as a y prime. And you're going to see right away here that this looks just like that. So we get 2y prime equals 1. If I solve for y prime, what do I get? I get that. Simple, right? That is implicit differentiation. You already know how to do a hard problem. Seriously, in fact, we could even do, everybody see that?
Yeah.
Okay, we could already do that problem if we wanted to. Let's do one slightly less difficult, and if we have time, we'll come back and do that one. But we could, seriously, we could do that. It wouldn't be that big a deal.
Wait, why is it dx dx? Why isn't it dx and y? Thank you.
Why isn't it what? Oh, why isn't it dx dy? Because we're not differentiating with respect to y. We're differentiating implicitly with respect to x. So that's really how we'd have to describe what's going on. The process of going from there to there is we are implicitly differentiating with respect to x. In other words, we're just
Looking at
taking the derivative of everything up there with respect to x. Same process we've always done. The only difference is we've got to use the chain rule whenever we differentiate something with a y in it. Because dy dx is not 1, it's dy dx. Right?
And implicitly means like.
Implicitly, all that means is we're not going to bother to solve for y first. We're just going to take the original relation the way it is and just differentiate. Okay? So let's try this. And you'll see that we can already do this. It's not that big a deal. So let's take something like, we'll make, nothing too horrible. How about if we try 3x squared minus 2xy plus 9y squared equals 3. And I want you to calculate dy dx. So let's find dy dx. But it's really no big deal. All we do is we're just going to differentiate everything term by term with respect to x. So what do we get from the first term when we differentiate? Yeah, that's an easy one. It's just 6x, isn't it? Right? Okay, what about this one here? Now, talk to me about the rules that we're going to have to use to differentiate that term. What is that? That's a product, isn't it? Yeah, it's multiplication, so we have to use the product rule. So we've got a minus 2 times whatever we get from the product rule. Okay, so what's the product rule going to give us? We've got first times derivative of the second, maybe, right? So x times y prime, good, plus y times 1, which we won't even write. Okay, plus, what about this guy here? Okay, so good, I've got a 9 out front. The derivative of y squared is?
18.
Good, so 2 times 9 is 18y, but I'm not, y prime, right? Because I'm not done. I have to differentiate this using the chain rule. There's 2 layers. The derivative of something squared is 2 times 9 is 18 times something, but then I have to differentiate the inside, and that's not 1. The derivative of y with respect to x is y prime. Okay, so you're starting to maybe see a pattern. What's on the other side, real quick?
Well, it has 0.
Yeah. Okay, so you see a pattern here. Every time, this actually works out pretty nicely. Every time you have a term with a y in it, when you do implicit differentiation, what's guaranteed to pop out somewhere? A y prime. Yeah.
By the end of the year, we're gonna be doing like differentiation with respect to y.
Oh, we could do it right now. Yeah, we will. I mean, we'll do that stuff soon. It's not hard. It's the same exact process as what we're doing now. There's nothing magical about y's and x's. We just because we call y the vertical axis, we like to write functions of x. But we could just as easily write functions of y and do the same stuff, very same stuff. Yes, you're right there.
Can you simplify it further?
Yeah, we would simplify, right, we'll keep going. We're not quite done yet, yeah, but the calculus is done. Now we're just gonna do some algebra.
Could you go on about 18 y prime?
Sure, because I had this 9 out front, which is just a constant, so we leave that out front. What's the derivative of y squared? Well, that's gonna be 2 times y prime, times 9. That's it, okay? We're not done though. If we're gonna solve for y prime, we have to now isolate the y primes, but that's easy, right? I mean, that's algebra 1 stuff, really. All we're gonna do is we're just gonna simplify by distributing, collect all the y prime terms on one side, the non-y prime terms on the other side, right? Factor out a y prime and divide by the rest. Every time it's the same. Now, the nice thing about this is, notice that this equation is easy to solve because the y primes are all linear. That's always gonna happen. Right? That's the nice thing about implicit differentiation. When you get down to the final layer, when you're differentiating the inside, the pit of the function, right, the very inside, it's always just going to be a y, and the derivative of y is a y prime. So the beautiful thing about this is you just get y primes multiplied in each term. It's not like you're going to have to deal with y prime squares or square roots of y primes. It'll never happen.
Can you go through it so we can see?
Yeah, so let's finish it up. So now we would distribute the -2, and we'd get 6x minus 2x y prime minus 2y plus 18y y prime equals 0. So we'll keep the y prime terms on the left, push the other terms to the right, and I would argue that very quickly, like after you've done maybe one of these, you can start to skip some steps. So if we collect the y prime terms on the left side, let's put the positive one first, and that's going to give us 18 y prime minus 2x y prime equals what? I'm going to get a positive 2y minus a 6x, right? Everybody agree?
Yeah.
Okay, I'll factor a y prime out of the left. And what am I left with? Equals 2y minus 6x. And then last step? Yeah, divide both sides by that factor, right? And I just get y prime equals 2y minus 6x over 18 y minus 2x. What's one easy thing I could do with this? Yeah, I could divide top and bottom by 2, couldn't I? Factor out of 2, top and bottom, and cancel is another way of thinking about it. So I just get y minus 3x over 9y minus x, okay? Couldn't we though probably really have just about gone, I would claim, from here down to there in almost one step? I think you can. I think you can, because look, you really think what you're doing here. You're just gonna say, okay, I know if I keep the y prime terms on the left, I'm just gonna factor out a y prime. So what are those terms? Well, that's gonna be a negative 2x plus an 18y, maybe flip them to put the positive first. That's always gonna be the denominator, because I'm gonna divide by whatever I'm left with when I factor out the y prime, right? What's gonna be the numerator of the other side? Whatever I get when I push these terms to the other side. So I can get right to there in one step. You see that?
Yeah.
I mean, you will. Trust me, as soon as you do this a couple times, you'll start doing that. You don't have to, but you might as well. Make sense?
Yeah.
Okay, so let's try one additional wrinkle to this. It's not a hard one.
That's the answer.
That's the answer. Yeah, that's the answer. So what if we want to do something like this then? What if we want to, let's see, let's do, okay, how about this?
Does stuff like velocity and acceleration still work the same way?
Yeah, same. Yep. Yeah, everything's the same. There's nothing really weird about this. It's just a different process. I mean, we got the same result. If you go back to that very first example we looked at, we got the same result either way, didn't we? Right? It's just that one way we did the hard way, and one way we used this shortcut. Which all it really is just using the chain rule, just differentiating right away. Right? It's nothing super mysterious, and you'll find right away that it's really not that hard to do. In fact, it makes a lot of things easier to do. Okay, so what about this one? What if we want to find the tangent lines to this curve at x equals the square root of 2? We can do that. So in order to find tangent lines, we just need a slope, right?
Yes.
Okay, so we can do that. We're just going to slope is a y prime. So let's just differentiate implicitly, because we have a y squared there, right? Or x is, how do we know when to do this? Well, if we have a situation where the y is very easily isolated, or maybe it starts off being isolated, we just normally differentiate like we always would. It's only when the x's and the y's get tangled up, where there's a y in there that you have to do something to isolate it, right? That's when we'd use this technique. So if we implicitly differentiate, what are we going to get here? 2x, you're right, 2x plus 2y, y prime, right?
Yeah.
Everybody see that?
Whatever.
Equals 0. Because we're differentiating everything with respect to x, right?
Oh, I feel you, yeah.
So now if we solve for y prime, couldn't I just divide both sides by 2 and get rid of those?
Yeah.
Right. So all I'm going to do is subtract the x and then divide by y, right? So y prime,
Negative x.
I mean divide by y, sorry.
I think it's negative, so we'll difficult design on that. We'll look at it.
So y prime equals negative x over y, right? Make sense? Okay, so no big deal. So then when x equals the square root of 2, we just have to figure out, just like before, like the same process we've always done. If we want to come up with the equation of a tangent line, we just need a point and a slope, right?
Yeah.
The derivative function is for giving us a slope, and the original relation is for giving us the y coordinate. If we have an x coordinate, we just plug it in and solve for y, just like before, right? So we've always done. Plug in the x value to find y, to get the y coordinate. Combine, that's our point of tangency. We differentiate and plug in the x value to find the derivative. Only this time, look what's going on. In our derivative, we have both an x and a y. That's okay. This isn't broken. This is allowing us to do something really cool here. If we take the value x equals the square root of 2, let's plug that into our relation. I was careful not to say function because it's not a function. Let's plug this in and solve for y. If we do that, we're going to get the square root of 2 squared is
2.
Good. So plugging in we get 2 plus y squared equals 4, right? So what are my steps to solve for y there? Okay, good. I'm going to subtract 2, and then I'm going to have to square root both sides, aren't I? So I'm going to get y squared equals 2. So therefore, y, oops, supposed to be blue, but you get the idea, equals plus or minus the square root of 2. Okay, that's important. That's telling us something really important here. That tells us that under the condition that x equals the square root of 2. So if I tell the math gods that, I'm telling you that x equals the square root of 2, you tell me what are the y values. They gave you 2 of them because there are 2. There are 2 points of tangency. The 2 points of tangency are x equals the square root of 2 and y equals the square root of 2. Or x equals the square root of 2 and y equals negative the square root of 2. Now that's important because that has an impact on our derivative, doesn't it?
Mm-hmm.
So in this case right here, so if we kind of divide this thing up, if we take this point of tangency, y prime equals negative root 2 over root 2, which is negative 1, right? Let me slow down.
So how did you get to the step where you put those into?
Okay, because right here, because look, this is y prime.
Yeah.
Right, so if we found that when x equals the square root of 2, when I plug that in and solve for y, I got 2 results. So when x equals the square root of 2, I can either get back y is the square root of 2 or y is negative the square root of 2. So I've got 2 different points of tangency. Let's forget about this one for the moment. Let's just look at the one where we get root 2, root 2. In that case, that's my point. My slope is going to be minus square root of 2 over square root of 2, which is negative 1, right?
Yeah.
And so what's my equation of the line going to look like over here? Well, that's my slope. That's my point,
Oh, okay.
right? So all I have to do then is just solve for b. So I get y equals mx plus b. Y is the square root of 2. M is negative 1. So this part right here just gives me minus the square root of 2, right? Plus b. So what's b?
0.
Well, if I add the square root of 2, I just get 2 times the square root of 2.
Which is 2.
No.
Wait, why is the square root of 2 negative on the equal side?
Because I've got a negative 1.
Yeah, but if you got that negative 1, wouldn't you have used that negative square root of 2?
No, I'm not even messing with that one.
Wait, then how'd you get negative 1?
No, that's okay. Let me show that step. I think maybe I skipped something there I shouldn't have. Let's do that again. So this looks like negative 1 times square root of 2 plus b.
So is negative 1
Right? Because
here?
this is x and y, right?
But how'd you get a negative 1 if you use the positive square root of 2?
Well, because
The original equation.
because that's my derivative,
Oh.
right?
Okay. What is the x over y then? I thought that was the slope.
It is negative x over y is my slope. But if that's my x value and that's my y value, then that gives me a value of negative 1 for
For
y
your
prime.
slope.
For my slope.
Okay,
Yeah.
that makes sense.
And it could
Right?
Mhm.
And so I end up with the square root of 2 equals negative the square root of 2 plus b. So I'm just going to add the square root of 2 to both sides and get b equals square root of 2 plus square root of 2 is just 2 times the square root of 2.
Oh, yeah.
So one line of tangent line is y equals
negative x.
negative x, good, plus 2 radical 2.
Could you go up a little bit?
Sure.
please? Thank you.
Okay?
Oh,
Oh,
are you gonna have this up tomorrow?
No,
No?
no, I will finish this up tomorrow.
Oh.
You see